And this is the bit where I say, can you see my screen?
Yep, we can see that.
Fantastic. So tonight I'm going to talk to you about IoT and Raspberry Pi, IoT being the Internet of Things, and a Raspberry Pi being a sort of handy development board that is in its fourth generation now and really popular. They've just got a whole load of new seed funding, about £30 million to take it to the next level. So this is clearly a device that's got some legs and it's not going anywhere. I'm John Staveley, I'm an MVP. You can catch me on LinkedIn or Twitter, and I'll be providing all the slides, code and stuff afterwards, and on LinkedIn and on Meetup. So my day job is I'm a contractor in C#, MVC, SQL, Angular, Azure, and IoT. IoT is a bit of a hobby for me, but it's turning into sort of fee-paying work recently for certain household name companies. I organise Lead Sharp, which is Yorkshire's largest .NET community, and IoT North, which is an IoT community of about 8,000 people that covers London to Scotland. I've used a lot of microcontrollers in the past, but I'm not an electronics expert. So one of the things I aim to do this evening is try and demystify some of the electronics for you and make it a lot simpler. So one of the things I'll be covering is how to set up C# on Raspberry Pi. So Raspberry Pi is a Linux distribution, and usually with Linux you do apt-get install .NET, but with .NET it's not that simple. But I'll be showing you how to set up .NET 5 on it. Then I'll be showing you how to control things. So if you, as I said in the introduction, if you want to control a cat flap, then you need some servos or some switches to detect whether it's open, or more complicated devices like I2C, like RFID, or a whole range of different things. You need to understand the different interfaces that Raspberry Pi offer. So we'll be covering GPIO, PWM, and I2C. Then, of course, once you've got your Pi set up and doing stuff, you'd like to control it from the outside world and also push data up from your Pi into a data center where you can digest it and display it on a website or something like that. So the intermediary I use is Azure IoT Hub. So I'll be giving a load of examples on how to use that and receiving updates from the device. So this is a Raspberry Pi. This is the version 4 of the board. So going around, you've got an Ethernet port here. You've got a couple of USB 3 ports, USB 2 ports, an audio controller. This is the display, the camera ribbon port, 2 micro HDMI ports, a USB-C port, a display port. Hidden under here, you can't see, there's a micro SD card, and that's what the operating system sits on. This is your Wi-Fi chip, and this is your CPU. And here are the all-important pins that we're talking a lot about today, is the general purpose I/O pins, and you also do I2C and PWM often. So you can do .NET on other embedded devices. There is also Meadow and .NET Nano framework on ESP32. I don't know anything about these devices because I've not used them, so I can't answer those questions. Maybe Pete can. So how do you get started? So one thing I would really recommend is there are lots of getting started with Raspberry Pi books out there, but the official Raspberry Pi book is very clear. It's idiot proof really, and takes you through baby steps, setting it all up in terms of hardware and software and programming. Other than that, somewhere like the Pi Hut or primarily do a Raspberry Pi starter kit, including a board and USB power supply. And it includes something like the Noob software, which is that Linux distribution of called Raspbian on a micro SD card. So all you need to do is plug it in, get the USB-C power supply, and you're ready to go. Now, I have a screen, a keyboard, and a mouse, but that's purely just to get set up on the Wi-Fi. Once I'm on the Wi-Fi, I don't need to bother with those at all because I then VNC onto the Raspberry Pi so I can see what's going on it. And it generally helps to have a fixed IP address for VNC and SFTP. So there's this guy called Pete who's done this really handy bash script that sets it all up for you. So I'm just referencing his blog post there you literally run that and .NET5 is installed on the Raspberry Pi and you're all ready to go. Some people install VS Code on the Raspberry Pi. You can do that. It's got a full desktop experience. I tend not to. I've got Visual Studio sitting alongside. I then publish to a directory and then SFTP those binaries onto the device. By default, it's secured by default, so everything's switched off. This is your desktop here. And then if you navigate down the menu, preferences, Raspberry Pi configuration, you'll see a load of everything's disabled. So if you fancy using the camera and you get a weird error message, then it's probably just disabled at this level. SSH is generally switched off, but you need a lot of these switched on so you can do some interesting things with it. So now we're going to talk about controlling the things. So first off is digital input and output. That's ones and zeros. The light is on, the light is off. Digital input, the switch is on, the switch is off. Analog input, the thermometer is showing 32.8 degrees centigrade. Pulsed wave modulation, so we're covering what that is. I2C, the hammer that drives in every nail, very useful protocol that can control a lot of really interesting devices like displays and the like. A little bit on the camera because the cameras are quite useful and really easy to set up. So in the .NET world, you'll be spending a lot of time in these namespaces here, and this is all open source. You can go and examine the source code and have a play with it and see how it works. So your base namespace is GPIO for binary inputs and outputs, and then with more complicated devices, you go into IoT.device.bindings. So I'll be covering those more later. And this is all about the pin layout. So all of these pins do different things. So up here, you've got two 5-volt power supplies, and then you've got two 3.3-volt power supplies. These can deliver quite a limited current. So a lot of the time, you'd use current limiting resistors to stop burning out the board. And then you've got general purpose IOs. So these are pins that can be configured as either inputs or outputs. So they either take inputs from switches and the like, or outputs like LEDs or display or some kind. So lots of different peripherals you can control with them. And lots of grounds. I don't know why they show so many grounds, but it makes it easier to wire up sometimes. So the hello world example in IoT is flashing an LED. So what you do here is you take one of the general purpose IO pins, you wire it up to a current limiting resistor via an LED, and then back again to earth. So this is breadboard if you've not, or VeroBoard if you've not met this before. So all of these pins here are connected together. So you've got a common ground, a common positive, and all of these pins are connected together. So that connects the yellow cable with the resistor pin. And then in terms of your C# code, you just define the pin number. In this case, it's 18, and then you create a GPIO controller, and then you set the pin to be an output. So I've defined that pin to be an output, and then you flash it high, wait a little bit, and flash it low. Easy. There you go. So there's your hello world in IoT. So the other things you can, lots and lots of different things you can control. So we've seen an LED. So there's another type of LED, a buzzer, an infrared LED. So something similar to like you have on a television remote control, a mini laser, not a high power laser. So you can project a small point on the wall. And this is a relay. So this is something useful for controlling large currents like electric heaters and fans and the like. And this is a multicolored LED. So these are 3 digital outputs connected to the GPIOs and a common ground. So you can flash it red, green, blue, or white, or any combination of colors you like. So the electronics can be quite intimidating. So there is some really good resources out there that I recommend you have a look at to try and simplify things for you. So this website here, I'm showing you an LED connected up here with a resistor. but there's a whole load of different things. So if I want to know how do I wire up a button, then that shows you there. How do I wire up a button controlling an LED? There are code examples. They are in Python, but you know, they're easily translatable to C#. This is the wiring I need for a servo. This is how I control motors. So it requires quite a lot of interfacing. So this is a really good cheat sheet for making the electronics simple for you. And integrating a lot of these components, you see a lot of arcane terms that you can really just get away with not knowing about, and I'll explain how. You need pull-up, pull-down resistors, anti-short resistors, anti-back EMF diodes. So for instance, on here, this is a relay control. You've got a GPIO pin and a positive and a negative. And you've got an LED to show that it's on, and a resistor and a transistor and a back EMF diode. But the point is if you buy a set of components like this, then you don't need to bother with all of that, because all of these peripheral components that are necessary but don't really add a lot of value to what you're trying to achieve come pre-packaged. So I'd recommend looking at something like this. So this is the Geekcrete 45-in-1 sensor module. So this is integratable with an Arduino or a Raspberry Pi. You've got a joystick, large sound sensor, small sound sensor, flame sensor, moisture sensor, distance sensor, memory card reader, moisture, humidity reader, real-time clock, laser. It's all set up, and this comes off Banggood, a Chinese site I use sometimes, for about £15. So really quite good value. And you see all the peripheral components that are pre-packaged for you and take a lot of the pain about doing electronics away. And then several people have written manuals on how, given you've got this package of components, how you wire them up correctly to the board, and then some code to use them. So there's an example there. As I say, I'll be sharing the slides at the end, so you don't need to make notes of the links. And of course, once we've got our board doing things, we want to control things. So the thing I use to do that is the Azure Internet of Things Hub. It sends messages to and from devices, and you can send 8,000 messages a day for free. And it's only when you get beyond that threshold does it start costing you money. You control 100 different devices. I'll be showing you how to control one device this evening. It's got event hubs, so that's where the 8,000 messages comes in. It's an industrial strength messaging hub. And you can support a number of different protocols, HTTP, AQMP, and MQTT. I think I'm using MQTT this evening. And it's got some advanced concepts like device twins. So you send it a JSON file, and then the code on the Raspberry Pi can be configured to respond to a change in state of the device twin. So you can then set itself up differently. And edge modules. So you can run Docker on a Raspberry Pi and then set up modules, Docker containers to do different things on that, including like Azure Cognitive Services. So, I mean, the setup of an IoT Hub is really trivial, and I'm not going to go through it because you need a name for the IoT Hub, and then you create a device in the IoT Hub, and you configure a direct methods, which then the device responds to. So I'll be showing how to do those later. Okay, so this is the IoT Hub. And this is my board. I'm introducing my board for the first time. So I'm just going to pop in here. So my Raspberry Pi is up here, and then I've got a direct method. So my direct method that I've set up to control the board is called just control action. And then I've defined a set of JSON. Set relay number 3 turns the light on. There you go. You see the lights popped on and then switched itself off. So just talk through what's going on there. So when my code on the Raspberry Pi starts up, which I've done before the show because it just simplifies my setup, it sets up a persistent connection to the IoT Hub. This Azure IoT Explorer is then an interface into the IoT Hub. So I send a message into the IoT Hub. My data center is in Cardiff, and that gets piped down the internet to this device, which is attached via Wi-Fi to my home network. And then it says, oh, I've got a new device. I'll switch it on and off. So the code on the client is really straightforward. So first off, I set up a device client and create that from a connection string, which I get when I set up to the IoT Hub. Then set up a method handler. So each time it receives a method, mine's called control action, it will fire this method called action method. Then I deserialize that into my control action, that JSON thing I sent you. And then I basically got a switch statement that says, well, if it's set relay, then do these actions. If it's get relay, then do these other actions. Do shout out if there's any questions, Pete.
Yep, I'm answering a couple in the chat here.
Okay.
You're on a roll. I was leaving you with it.
Oh, okay.
Yeah, Arnaldo's asking about is there some code there to be able to handle things like stepper motors? So I've just pointed him towards the IoT device bindings library for .NET, which is fantastic. It's got, I don't know, must be 40 different devices in there, including servos. And I would say a stepper motor as well, but I'm not 100% sure. I'd need to look.
Can you use PWM for stepper motors?
Possibly, yeah.
I think you can.
Yeah, I know you can for servos. I've never used a stepper motor as it happens, but you probably can.
Well, I'll be doing a section on servos. So tell me if that answers your question, and I'll.
All the devices are in the chat. No. I'll carry on. You carry on.
Okay, cool. Right. So a little bit about the development experience. So I develop in Visual Studio, rather than some people develop in Visual Studio Code on the device. What that means is you have to publish to a directory, and there's some key properties you have to set on the publish to make sure that when it gets published to a Raspberry Pi, the Raspberry Pi understands what it is, because it doesn't understand a Windows executable, strangely enough. So you just need to set the target runtime to Linux ARM and the target framework to .NET 5, which you've previously installed using Pete's fabulous script. As I said before, fixed IP address helps because then your SFTP and VNC to the same place each time, and you don't have to set that up. And then you need to configure the binary that you just put onto the Raspberry Pi so it's actually executable. So there's a chown and chmod commands that you need to do that. So my executable is called control chown and the user's pi, so that gives it access and executable privileges on it, and then I can instantiate it and it'll work. So a few examples of digital inputs. We've done the flashing lights. So you've got a push button, which I'll be demonstrating later, a read switch. So if you've got an alarm system at home and you've got a window contact, so there'll be a magnet on one side and one of these read switches on the other. And when the magnet moves away from the read switch, it breaks the connection and it moves back in, it joins the connection. So it's a switch that's activated by a magnet. Here is a Hall effect sensor, so it detects magnetism. And then here you've got three different types of movement sensor, a tilt switch, a ball switch, and a knock sensor. So for instance, detecting whether your cat flaps in the vertical or horizontal position. Quite a good sensor there. Light blocking sensor. So if you move a card through or block this, there's a transmitter and receiver on either side of there, and it breaks or makes a signal. And an infrared receiver to map to the infrared transmitter we saw on the previous slides. If you've got a motion sensor at home as part of a home security system, for instance, this is what will be in it, one of these motion sensors here. the text body heat. Now on to pulse wave modulation. So here you've got a different kinds of duty cycles. So it's the degrees of onness or offness. So something's pulsing out a signal out of one of the pins, and it has this profile. So a 0% duty cycle is 100% off. 100% duty cycle is 100% on, and a 50% duty cycle is 50% on, 50% off, 50%, and so on. So there's various devices out there that respond to different pulse widths. So an example is like a dimmer light. Here is a dimmer LED. So you can see as the duty cycle is increasing, the degree of onness of the LED is increasing, and as it decreases, it goes off. But more important than that is servos. So these servos have got little motors in them, and as you change the duty cycle, it goes on and then off. Okay, so I'm going to do a quick demo. Right, so this is a continuous servo. So what I'm doing is increasing and then decreasing the pulse, and that's setting the continuous servo to either move slowly in one direction or fast in one direction. So this is really quite useful for robot wheels and the like. And here you've got a pan and tilt. So this is the kind of thing you'd have in a CCTV camera, where you've got one servo to control the pan and another servo to control the tilt on the top here. Here we're panning backwards and forwards. That didn't work. Okay, there it is, panning away nicely. Tilting rather. There you go. Okay, so that's pulse wave modulation. This presentation works better if you're all face to face, because then you can. It seems more real to see this board trundling away in front of you. And they're the PWM pins. So you've got some hardware-based PWMs, and you can control two different devices from those pins. So examples of things you can control using pulse width modulation. Servos, continuous or directional. So you saw an example of a continuous servo there that changes speed and direction based on the pulse width. Lamps or LEDs, classic dimmer switch, motors, pumps, fans, display dials, and lots more. So this is a YouTube video of someone who's programmed in PWM to play the Star Wars theme tune through the speaker. So that's just quite a cute example, I thought.
Yeah, I did that. I gave it as a wedding present to geeky friends with an Arduino rather than a Raspberry Pi, actually.
Oh, very good.
Yeah.
Cool, and that's how you configure a servo. So you just give it a positive and a negative, and one of the PWM pins to control the pulse going out. And it's really simple to set up. So you just declare a software PWM channel on pin 18 with a frequency of 400 and an initial duty of 90%. And then you just set to start, and you can change the duty cycle between 0 and 100. I would recommend hardware PWM over software PWM. Software PWM is simulated, so you can use it on any pin, but basically you're reliant on the operating system remembering to send the pulse down at the correct time. And as we know, operating systems can get distracted doing other things, whereas the hardware PWM doesn't. That's all it does. So I find this a bit stuttery. And there you go. There's a directional servo going backwards and forwards. So this would be useful for controlling your cat flap or your canary box, or feeding your cat, or whatever it is you want to control. And then there's a pan and tilt. Cool. So I2C is where things start getting fun, because like when you've got a hammer, everything looks like a nail. When you've got I2C, it's like, oh, I can solve that problem using I2C. This is where you get a lot more powerful devices you can control. So basically, you've got these two data lines, data and clock, and I2C stands for integrated circuit. It's two-wire communication. You've got two sets of I2C ports. It's good for short range, but you can control multiple devices. So on my demo board, for instance, I've got chained devices all working together, but it won't work over like tens of meters or even meters. It's got to be short range. You need to enable it on hardware. So that security screen I showed you at the start, and there's some really good Linux tools to show you what devices you've got connected. So apt-get install I2C tools, and that will show you which connected. So sometimes that's useful for diagnosing connectivity problems. So the kind of things you can control using I2C. A relay controller, which I'll be demoing later, as with PWM controller. This and you've got digital I/O expansion if the Pi doesn't come with enough I/O for you. This LCD screen is I2C based, so you just send pipe commands down the line, and it displays different messages based on you. Apologies for the poor quality video, but it's an animated GIF. Analog inputs, which I'll be demonstrating later. It's the GPS module, so if you want to know where you are in the world, RFID tags, so you can program tags and then get this device to respond to different inputs. A rotary encoder, which is basically a volume switch, a temperature, pressure, humidity sensor, which I've got set up on the board. Accelerometers, memory cards, yeah, you name it, the list goes on and on. So as an aside, you start throwing components onto a board, and it starts getting complicated. So you need lots of these jumper cables to connect things. So this is male to female jumper cables. And this gives quite a strong connection to the pins on the board. So, I mean, I've lugged this board all the way to Liverpool and back in a couple of weeks, and the pins don't come out. So it's really useful for not losing your hard work connecting things up. Also got DIN rail mounting. So this is good for making connections. So I connect the major voltages using these and make sure that those don't fall out. As you can see, just you can connect quite a high current through there. Breadboard, as you've seen, is good for rapid prototyping. They don't have such a great grip on the pins, so occasionally they fall out. So we need to think of some other way of holding everything together. And then what I call posh man's Lego, you sort of hold everything together on the board. So I use this totem maker stuff. So on my board, which I've shown you before, we've got some connector blocks here. So the mains voltage comes in here, and I've got two transformers on here, one 12 volt and one 5 volt. This is quite meaty because it can deliver 4 amps. So I can control some really quite high powered devices like the solenoid and the lamp for this thing. This is for feeding the Raspberry Pi. The Raspberry Pi is hidden under here. This is a relay stack. So these voltages come out here and then connect different ways through these junction blocks. Then I've got the totem maker. So I've got a little BME 280 there. That's the temperature and humidity sensor. Analog inputs and outputs. This is a servo controller, and with all the servos connected, so nice and neat. They don't fall all over the place. And this LCD controller. So this is really useful. So keeping everything together. And the bedrock of everything is these DIN rails here. So if you've got an electricity fuse box in your house, all of your fuses will be mounted on rails like this. So this is a very standard interface design, and you can get power supplies and connector blocks that will interface just with these DIN rails, and it's good for holding everything really securely together and doesn't fall out. The only weak point I'd say here is these wires. So these wires are not designed to do this, but I just thought I needed a variable resistor in my circuit, so I've chucked it on there, but these wires do fall out. They're not proper jumper cables like here. But once they're on there, these things don't fall out. They're pretty sturdy. So it's really good for prototyping and holding your circuit together. Okay, so now I've got my I2C interface here. I want to control some things with it. So I'm using a PCA 9685. So this can be used to control any number of different PWM devices. So here I've got set up a servo. And as well as positive and negative, you've also got the standard clock and standard data lines going into the Raspberry Pi. And that can control up to 16 different devices. And in fact, you can stack these 36 of these devices to control 36 times 16 devices if you want. Now, the Raspberry Pi can't deliver that much power, so you've got this supplementary power here. So that connects direct to your power supply. So here you can see it's set up. It's connected to my Raspberry Pi here. So positive, negative, standard data clock. And these are control. All these lines here are going to these devices over here. All these different PWM devices. And then the coding is really straightforward. So the devices.iot page that I showed you earlier has got all those, all of the devices set up. So you just create a new instance of it, click reset, and then set the duty cycle on the channel you want. And it sends all of the bits and bytes down the wire at the standard data and standard clock, and then the device knows what to do with them. So you control lots of different devices really simply using very little code. Now, there is lots of beautiful hardware out there. Now, if you go onto the Pi Moroni, which is a great website in Sheffield, you know, you can deploy rainbows. You've got this beautiful ink screen. You've got different hyperpixel displays, LED displays. But I would advise some caution here, because not everything you see in the shop you can use, and that'd be as true as if you're just doing, you know, standard C on an embedded device or Python on an embedded device. You need to think, well, there's everything that the Pi Moroni shop stocks, and then I need to find out whether it actually exists in my namespace. So this is the IoT documentation here, and it says, well, these device bindings, you can control analog digital converters, accelerometers, gas sensors, but only of these types. So what this means is someone's written an interface that pipes the bits down the I2C cable and then can control this device. If someone hasn't written an interface, then it's a lot harder. But it's not impossible, and I'll explain in a moment how you do it. So you've got light sensors, barometers, altimeters, thermometers, gyroscopes, compasses, sonar, distance sensor, loads of different displays. You've got quite a lot of flexibility. But the bottom line is not everything you can buy is what you can control natively. So you need to think about it. So there's that documentation. So when I bought this relay driver here. So that's just a hat that sits on top of the Raspberry Pi. And then I looked at it and thought, oh, it's got a Python driver. Generally, when you look at components, they've got a Python driver, which means it was written to use with Raspberry Pi, or it's got a C driver, which means it was written to use with Arduino. Rarely has both, and sometimes has a C# driver. So I needed to so what I did is I took the code, which is written in Python, and then stuffed it through a Python translator that I found on the web. The only bit I then needed to do is then attach the I2C interface, and it's a way of interacting with I2C on top of that. And then it does all these bitwise operations, which I don't really understand, but I don't really need to understand how they work, because it's been written in such a way that if you translate it correctly, it just works. So I changed the names, changed the method declarations, and it all seemed to work fine with minimal code changes. So yeah, that's a relay hat, and you can control all sorts of different things with it. So a relay, depending on the rating of the relay, you can control 1 amp or 10 amps. So you can control, you can set a bar fire to come on and off with one of these things. You can control solenoids, which I'll demonstrate in a moment, high ampage lamp. You can, or even set off fireworks, which used to be part of this presentation, but it scared someone in the front row, so I don't include that anymore. Okay. Okay, so there it is. That's, if you heard, you could just about hear a little click in the background. That's the electronic switch going on and off. And if you watch this bit here, oh, so what this is a solenoid. So this is wires all wound round, and it becomes an electromagnet. So when you put a high current through it, it causes that bar to slide across. So these kind of things are useful for electronic doors and controlling electronic bolts. There you go. So that's my I2C relay hat. And you can see it switching on and off, flicking across. And then the code's really simple. Because I translated it, the type system's not very pretty, but it works. So it just has a method called set relay and then get relay. Now, I want to do a quick introduction to Blazor at this moment, because now we've got our Raspberry Pi and it's got some useful things hanging off it. We want something to control it, and we also want to receive telemetry live back from the Raspberry Pi. And I'll explain why Blazor solves that problem. So Blazor is a SPA application framework, a single page application framework. This version of it is just server side, which means all the code's running on the server rather than C# code running in the browser, which is sort of fairly standard example you see at conferences. And it has push updates by SignalR, which means if I change a property in a web page, it then will push an update down to any tenants, clients of that page. So if I've got 100 people looking at that page and I update a property that's linked to a div, for instance, they will see that div update in their browser, be it on a PC or a mobile phone. So for instance, my application looks like this. It's got a select box, which is backed by a property, a button, which is backed by a method, and then I've got somewhere to put output. So in terms of a button, it just binds in this way. You've got this ampersand on click send message. So in the page behind there, it feels a lot of like ASP web forms, but it's a lot better. You've got a method called send message. So when I click this, it instantiates that. So there you go, as the method it calls. And then I've got a div here, and the class and the message are controlled by these two properties. So when I set the message to be an exception occurred, and then the message class to alert danger, because I'm using Bootstrap, it will appear to any clients of that web page. So it changes the message and changes the color. Now here we get a service connection string. So before I demonstrated a device connection string, the service and device connection strings are different. Save a couple of hours of your life and know there's a distinction, because I didn't, and I wasted a lot of time. You get a weird error message and it doesn't tell you that why the device connection string doesn't work in a service client manner. So then I set up a device method. So in my case, it's called control action. And then I serialize my control action package to JSON. So I've got a control action class that serializes to JSON. Then I set the payload and then invoke the device method. Okay, so we're watching this LED come on here. It goes red, blue, green, and then white. Yeah, so that's a pretty good example. So what's happening here? So so this is my Blazor application. So when this is instantiated, it creates a persistent connection into my data center and the IoT hub. When I click this button, a connection from my signal R message from my browser is sent up to the Blazor application in my data center, which then sends a message to the IoT hub, which my Raspberry Pi is subscribing to updates from. So then it goes, oh, I've received a message and I can do some action based on that. Now, so if you see that there, so this has gone all the way to Cardiff, Azure West, send a message to the IoT hub and then send a message back again. Down to the Raspberry Pi, which then causes the solenoid to flip over. So a quick mention of the camera. So you've got a ribbon cable like this. It's very easy to interface as long as you get the ribbon the right way around. It doesn't work the wrong way around. You've got a basic camera here, a high definition camera, and a nighttime camera, infrared. And they're very easy to interface with a couple of lines of code. There you go, all fits nicely. Now this is a quick digital input example. So here you've got an example of a rate limiting resistor. Again, if you take the Banggood package, this is all on the board, so you don't need to bother with this. And all you do is connect a positive to a GPIO and then configure it. So I create and set input pin -22 and a GPIO controller and define the input pin as an input and then do a read of that. So what I'm going to do here, this is a button and I want you to watch what's going on here. Okay, so what was happening there? So every quarter of a second, my Raspberry Pi was going, has the state of the button changed? Has the state of the button changed? If it detected a state change, it would then push a message up to IoT Hub. IoT Hub would then notify all subscribers, in this case, my Blazor website, that a change occurred and send a message to it. The Blazor website would then send a message to all of its subscribers via signal R that something had changed, and then my div down here would change, would update. So you can see that happened incredibly fast. even with the artificial wait of a quarter of a second for the state to change, it's pushed up to the data center and then back to any subscribing devices really quickly. Oops. Okay. So a couple of analog input examples. Potentiometer, which is like a volume control, thermistor, which is a temperature sensor, a pressure sensor, light dependent resistor, a force sensitive resistor. So like basically a burglar pressure pad, a distance sensor. So this is something that's like on the back of your car and detects whether you're going to reverse into someone and bleeps at you furiously when you're about to, or even if you're far away. Magnet sensor, a sound sensor, and a flame sensor. So I've got to try and remember. So here is my ADS115. So this Raspberry Pi don't do native analog inputs, so it relies on this component here connecting via I2C to get analog inputs. I don't think it's connected up. I'm trying to remember which pins it was connected to. Right, so this is a light sensitive diode on pin 3. So if I cover it up, I would expect a small difference in the, maybe it's not this pin 1, sorry. So as you can see, the voltage is changing when I cover and uncover, and that's how you do analog on a Raspberry Pi. There's the ADS115. Again, you've got an I2C connection, data and clock, and ground and voltage, and you can connect up to 4 different analog devices like a voltage switch or magnet sensor, or in my case, a light sensor. If you want to push updates, then you can configure it to have an alert that when it reaches threshold, it pushes an output there. So you can take an input from it on the Raspberry Pi and then trigger something based on that. So this is the case when the Raspberry Pi is talking to the event hub. So this is my message, my button on the Blazor side. Just create a device event and then serialize that device event to JSON and send that. So that will contact the persistent connection that I make with the data center and send that message to it. And then any subscribers to that can then act on that. So the IoT Hub is backed by Event Hubs, which is an industrial strength messaging system. It's scalable to millions of events per second. It's basically Kafka as a service behind the scenes and supports a number of different protocols. And as I've shown, this is how it works. The Event Hub can have subscribers, in this case, my Blazor site. I need to disable the default routing so it actually goes somewhere. And in that way, I can receive a message from the Event Hub. So this is my subscriber in Blazor. If you've used Kafka at all, it doesn't delete messages. It sort of has a marker. So, you know, I've read up to a message 1,000. I've read up to message 10,000. It's always scanning forward, and it keeps those event markers in blob storage. So that's why you need the storage client here. Then you set up a consumer client and an event processor, and then you create these methods that are subscribers to any events that are received from the Event Hub or any errors that are received from the Event Hub, and you start processing. So the process event, so when it gets sent a message, this this code is instantiated and executed, it then calls this method to any of its subscribers, in this case, the web page, and then it updates the div on that web page. And then you just say, well, I've read up to message 100, 101, etc. So all of that code's in GitHub. I'll be giving you the links to that at the end, and I'll also put it on Meetup tomorrow. So I receive a number of different events from the device. So when the device starts, it pushes the message up. You may have noticed that every 2 minutes it says, I'm alive. Here you go. Device is still live after 68 minutes, and this is the temperature and pressure. That button push example that I've demonstrated, and you can also have light sensors. So it's extremely powerful, the Raspberry Pi. You can control lots of different things with it. If you've got one before, I advise you to get it out of its box and give it a play with. It's really straightforward and simple, and feel free to steal the code that I'll give you. You can control lots of different things, digital inputs and outputs, so switches on and off, lights, or taking data and telemetry in. You can take analog inputs like volume sensors or thermistors, pulsive modulation to control servos, I2C where you can control all the things, lots of different camera types. Not everything you can buy can be controlled yet, though hopefully some of the things I've demonstrated will make the electronics simpler for you. And then finally, Azure IoT Hub can be used to connect to and control your device from the internet and receive live events from it. So there's a couple of resources. Pi Hut do a really good starter kit that sets you up. The how-to book's really good, and the 45-in-1 sensor pack. And there are some code links and the slides if you have any questions.
Very good. I mean, I've seen that talk before, but it's still good.
Thank you, Faisal.
That might be the third time I've seen it now, actually.
Really?
Yeah, well, you've done it at .NET Knots, haven't you? And I'm pretty sure I saw it somewhere else as well. So, in fact, you might have done the lightning talk version of it.
Okay.
Possibly. Yeah. Either way, I've seen it at least twice now. It's very good. Thank you very much. So, questions in the chat. I
haven't followed anything in the chat, so
that's all right. No worries. I think I've answered a lot of the questions before from Aldo, so thank you for those. Kay, how long can be working alive a Raspberry Pi with a similar configuration? My question is regarding on temperature. So how long can it stay up for?
This I have not tested. I would say the Raspberry Pi does expel a lot of heat. This is not something you're going to run off a battery for very long. Yeah, I mean, I think it can stay up a very long time. I haven't heard of anything that says, as long as you keep it like any computer, reasonably cool and reasonably dry, I think it should work for a very long time.
Yeah, I mean, I've got one that's a file server in my office, and it stays up for, I think it stayed up for a year, all on its own. But generally, people will set up what's called a cron job on the Raspberry Pi just to reboot it every 24 hours. So if it's something a bit more production-y, although a lot of people don't like and don't advocate for Raspberry Pi in production, but yeah, that's certainly what I would advocate if you want to make sure that it stays up longer. Like John says, it's a computer. It's eventually it'll slow itself down to a crawl and crash. So yeah.
Yes. Yeah. The other thing I don't like about Raspberry Pi is you have to give it a controlled shutdown. So with an Arduino, you can just yank the power out, no problem. But if you do that with Linux too many times, it won't come back up again once. Yeah. Now, having said that, I have pulled the power out on quite a few occasions, and I've got it back up again. But the first thing it says in the book is press start, shut down. Do not do it any other way. Continued happiness.
Yes. Well, obviously you can do it from the command prompt as well, just as easily, but the same idea applies. John's right. Yanking the power is often bad for the SD card. Yeah. So obviously feel free to come off mute at this point, and you can shout out your questions, and John will do his best to answer them. you've blown everybody into.
Yeah, if anyone wants to
oblivion.
discuss their pet project they're thinking of creating and how we'd solve that in hardware with hardware and electronics, then feel free to get some free consultancy.
Yeah. Oh, Alan, did you have a chance to play with your and I can't even remember the name of the device that I sent you. It's like a Seed Studio thing. I can't remember what it's called. Alan's gone. They've all gone. They've been swallowed up by a black hole or something.
If Alan's gone, it means he can't win the Twitter prize. So get your tweets in now.
Oh, quick. Yeah, you've got a good chance now. I've not even checked the hashtags, actually. Have you checked, Jess? No.
I haven't, actually.
Let's have a look. Latest on it.
You think children interested in IoT? Yeah, I would start them on microbit first. And I don't know how old your children are. You can put the ages of your children in the chat now. Yeah. 8. Yeah, so my daughter's 8. She was doing microbit at 6. She could still do microbit now. I would recommend Scratch Junior first, and then Scratch. Well, that's just web-based. That's not IoT, but it's a good introduction to programming, and you can go to JavaScript and Python straight from there. There are some great children's coding books. Yeah. Peter, you got any suggestions?
One of my workmates is doing Jawbots with his daughter at the moment, because you can do like secret codes and stuff, and that's all based in Python.
Ah, okay. Not heard of that. What's it called?
Jawbots. I'll find a link.
Not heard of that before. Yeah, that's new to me, so thank you for that one.
Yeah, I mean, microbits, it's really great. You've got the use case with microbit is that you don't want to do any of the electronics. So all the peripherals are on board. You've got buttons, you've got tilt sensors, you can got temperature sensors, you've got expansion packs that are really straightforward. You can control robots, LEDs, all sorts.
Yes, that's good. Microbit's actually quite a powerful device. Once you, it's got the same I2C and SPI interfaces on it, and you can plug in all of the stuff that John was showing you there. And I made like a fake Enigma machine using one that had a full QWERTY keyboard, which you can imagine. Microbits are tiny little things, but actually quite powerful under the hood. It's got BLE on it and radio.
Oh, yes. So if you've got two microbits, you can get them to talk to each other. So if you've got 2 children, one can code and send messages to the other one, and they can display on the LEDs.
Yep. Yeah, I actually suggested that to Arnoldo there because he was asking about radio for the Pi. And actually, that's a really affordable, easy way to add radio to the Pi, because the microbit's got a serial. If you plug it in with a USB, it gives you a serial port, and you can communicate between the Pi and the microbit that way. I did a little proof of concept doing that easy. But only about 10 or 12 quid for a microbit, you see, and comes with everything you want.
Yeah, if you live in Leeds, you can go to the local library and you can check out the microbit and the power pack for free, and how to program book. So it shouldn't even cost you anything.
Obviously, you've got to give it back. It's frowned upon to keep it.
Throwing some links into the chat. One for Pimeroni's microbit shop, but they also have like a little kit shop as well with various different bits of IoT that you can start kids on.
Yep.
We may have also bought these for conference swag at some points.
Yeah, I wouldn't recommend Arduino because you have to program in C, and it makes me cry sometimes. Raspberry Pi, yes, because you can do Python, also Scratch on a Raspberry Pi, and then control the peripherals. Obviously, the interfacing is a bit more complicated, but you can buy like hats like this for your Raspberry Pi. So it's got a 3-color LED matrix. It's got a joystick. It's got temperature, pressure control. So this is the thing that Tim Peake took on the space shuttle, the space station. Another number of other things. Sense hat. Yeah. So that's all controllable via Scratch.
Yeah, that's an awesome project. That is. Yeah, Sense Hat, that is, Arnaldo, part of the Astro Pi project. So they've just sent 2 new Raspberry Pi 4s up there, but originally there was 2 Raspberry Pi 2s with that, the Sense Hat. I'll send you a link to that. Jess, that link you put in there for Pi Moroni is fantastic. I'm a big fan of Pi Moroni and Pi Hut, to be fair.
Yeah, I advise caution when shopping with Pi Moroni. You can spend a lot of money.
Just advise caution if you start listening to people like me and you.
Yeah.
Gets expensive. Fun though.
Yeah, only buy one peripheral at a time, then use it, and then move on.
Yeah. I've put a link to that Sense Hat there in the chat as well. Yeah, that's well worth checking out. Actually, the Sense Hat is sort of like bolting on the most part of a microbit. That microbit has got a very similar set of functionality to the Sense Hat.
The Raspberry Pi website is really good as well. It gives you like step-by-step tutorials with lots of nice pictures of kids having fun and doing stuff, and looks really good.
Yep. I mean, there are also some learning resources for children on the Microsoft website as well. The MS Learn site has got a specific Python set of modules in there angled towards space, and they're dead good as well. But Python programming is possibly for an 8-year-old might be a bit too much of a step up. So John's right.
No. Yep. They have to get the concept of indenting everything, and it just, what's white space, Daddy?
Yeah. But there is if you're interested in teaching them electronics as well, AutoCAD have got a free site. You just have to join it, and you can drag electronics onto a designer and hook them up. And you can hook an Arduino up to it as well. And the good thing is you don't have to program it in C. You can program it in a Scratch block-based language. So I'll put that. It's called Tinkercad. And it's awesome. So I'll put a link to that in there as well. And the great thing is you can download the code you create in blocks, and it'll download the C equivalent of that code, and you can then just program it into your Arduino, wire up the circuit you've made virtually, and it'll just work theoretically. So it's pretty powerful stuff actually, and free, which is amazing. And the microbits in there as well.
A little bit away from IoT, but Minecraft also have their own equivalent of Scratch. I don't know if anyone's seen that.
Mm-hmm.
I installed Python on my daughter's machine that she uses to play Minecraft, so she can now like do /pi castle, and it will build a castle with moat and Mott and Bailey in like a second, and suddenly an 8-year-old who just wants to play Minecraft is interested in coding again.
I like that. That's another good link from Jess there as well. Code Builder. That's great. I've not seen that, Jess. That's awesome.
I have a lot of workmates with kids who are very bored at the minute.
I like that. I'll have to show my daughter that one.
Yeah, so it looks a lot like Scratch.
Yeah.
Good stuff.
Yeah, that's awesome. There you are. You should have enough to be getting on with there, William. Yeah, exactly. You're going to be very busy.
Yeah, try one thing at a time.
I mean, for the microbit as well, the good thing is Make Code, Microsoft Make Code, which again will use that block-based language, and that's got a simulated microbit to the left, and you can even simulate things like the radio directly on there, simulates things like servos directly on there. You don't have to build a thing. And again, you can just press the download button, program it onto a real microbit, and off you go as well. So yeah, I'm a massive fan of the microbit. I think it's awesome. And not just for children, for adults that are interested in dabbling with IoT. Like John says, it's got a bunch of functionality already on the board, so don't need to hook any electronics up even.
Kind of hoping that Hackspaces will open again, because they used to do some great, like, you could go and spend the afternoon and learn microbit from other people, or just sit there and hack.
Yeah.
It used to be a lot of fun.
Yeah, the one in Nottingham is lovely. So I don't know if it's even still open.
They were doing a lot of initiatives over the pandemic for refurbishing laptops for those who couldn't afford them and needed to work from home and things. So I'd be surprised if they're not still going.
Yeah, I would be then. Right, I'm going to turn YouTube off at this point. We'll carry on. No need to disappear off.